Fink from Queen Mary University, and he will talk about tropical differential equations and their solutions.
Right. Thank you, Jerome. Let me try. Okay. Is the screen sharing working?
Yes, it's fine.
Yes. All right. So thanks, Jerome and Andrea, and thanks everyone for coming. And welcome to my lo-fi board talk approximation on tropical differential equations and their solutions. So my talk is about the theory of tropical differential equations as introduced by Dima Grigoriev in 2015. He was interested in complexity theoretic questions and then developed by others since, in particular Fuensanta Roca, Christian Garay, and Zainab Tourani in 2016 published a theorem, a fundamental theorem relating differential equations with solutions in power series over a field to a tropical counterpart thereof. Zainab was my postdoc, and so we have worked some more on this area, but I thought today it would be best if I present that fundamental theorem and also a recent multivariate partial differential generalization of that fundamental theorem. So if there are results with my name on them, they will arrive late at the end, if at all, after the main results. But this should hopefully be useful warm-up for Jeff Jandrekuza's talk and for Stefano Moreto's poster, which are to come. So, all right, I'll start with a bit of setup. So the work that I'm talking about is all done with differential equations over fields of characteristic 0, where we're interested in power series solutions. So that's the setup we're going to use. Part of the development that we'd like with this theory is ways to generalize these constraints, maybe to globalize it to differential geometry of some sort, or to work with p-adic derivatives. But as this is all set up, so we have a field of characteristic 0, and it takes place in the power series ring, which I'm going to call R sub m as the power series ring in m indeterminates, T1 through Tm, or for short, I'll just say K adjoin the vector of T's like this. This is, of course, a differential ring with m derivations, the usual d by di, or d by dti. So just a set notation. So this will be our base ring. It's not a field. The theory is somewhat awkward for Laurent series, so we're going to stick with this ring as our ring of coefficients. Some of the results will require m equals 1. Some are valid for more general m partial differential equations. So the differential equations themselves live in a ring that we get by adjoining differential variables to this. So the textbook notation for that is to take this ring and then adjoin differential variables, x1 through xn, say, and again, I might want to abbreviate this as adjoining a vector of x's. Well, what is this thing going to be? If I adjoin a differential indeterminate, then what I actually want to do on the algebraic level is adjoin naturals to the m different indeterminates. So for each differential indeterminate, x1 through xn, I want to have a formal derivative of it given by applying any composite of these differential operators. And so J indexes which differential operator I'm applying, and it lives in naturals to the m. This is also a differential ring by extension of these di's in the expected way. So if I apply di to some x, let's see, if I apply di to xkj, what I get is k comma j plus ei, where ei is the ith standards basis vector. So these xij's are just formal derivatives of these xi's. So that's my notation. Extended by the Leibniz rule, of course. So that's the classical setup as found in textbooks on differential algebra. On the tropical side, well, in place of rings and fields, we take the kind of usual approach of using idempotent semirings, idempotent semifields. So semiring, semifield means we don't require the additive inverse law. Idempotent means that instead A plus A equals A. So the tropical side, we have the idempotent, Boolean idempotent semifield is where I'll start. So I'll denote this thing with Blackboard bold B, and its operations just as plain plus and times. So this is the Boolean idempotent semifield. And rather than the kind of tropical flavor notation, I'll just denote this as 0 and 1. So 0 is its additive identity element, 1 is its multiplicative identity element. Since it's idempotent, 1 plus 1 equals 1. So that's the smallest semifield, and I will be using this to replace the field k, as it were. So all of this is in terms of the trivial non-Archimedean valuation on k, if you like. So I'm going to build the algebraic apparatus parallel to what I've just done. So now I also have a power series ring in B, an idempotent semi-ring. An idempotent semi-ring, where the operations can be defined as you expect. Right? These are power series with 0, 1 coefficients. And so isomorphically, if I have a power series in here, I can look at the set of monomials and the t's that actually appear, the set of places where the coefficient is 1. That's a subset of the exponent vectors, a subset of the possible monomial vectors. So I can present this semi-ring isomorphically. The elements are just subsets of m tuples of natural numbers. The addition becomes union, and the product becomes Minkowski sum. So if you're used to the sort of polyhedral perspective, that's isomorphic to this semi-ring of power series and m variables. So I can define that idempotent semi-ring, and similarly I can define another idempotent semi-ring where I join the differential variables to it, which will mean the same thing. This will be the same as if we join algebraic indeterminates xij, where the I and j are as above. I indexes which differential variable, j indexes which formal derivative of it. So those are the tropical algebraic objects that we're going to be working in. Up here we have differential rings. Do we have differential semi-rings down here? Well, I'm not going to take a stance on what a differential semi-ring should be. I believe this is something that Jeff and Stefano are going to say more about. But for my purposes, all I'm going to want to do is define a function which behaves like a derivation, or which is defined by analogy to a derivation on this semi-ring of tropical power series. So I want to say, just define a function di from this ring to itself, semi-ring to itself, that acts sort of biparallel to the way it acts on power series over a field. So if I have, let's say, alpha sub a t to the a, where a indexes the exponent vectors, what I want to do is just say, well, drop the vectors where, alpha I is greater than or equal to 1. Sorry, no, ai is greater than or equal to 1. Drop the exponents vectors, which had a 0 in the ith coordinate, decrement the exponents in every other place, just leave the coefficients alone. These are 0, 1 valued coefficients. You know, I'm not multiplying by AI or anything because I'm using the trivial valuation. So I'm just shifting this whole power series. These DI become shift operators. And as I say, you can write down some kind of tropical linearity condition, tropical Leibniz rule that these satisfy. And it does satisfy if you write down the naive thing, but that's not going to be relevant here. For these purposes, it's just a set function. That's all I need. Actually, I guess I do want to say one thing about it, which is, well, I've set up the characteristic zero thing, I've set up the tropical thing. How do they relate? Well, the main passage that we're going to have between them is, well, a tropicalization. If I have a power series over a field, then I want to, as it were, tropicalize it coefficient-wise with this trivial valuation. I'm going to call that the support map because that's what it amounts to. So I get a support map from, well, to remind you, this is my power series over a field mapping to the power series over the Boolean semi-ring. And this just says that if I have some power series over a field, well, I get 1 if the coefficient is non-zero and 0 if it's 0. So using these, I will want the observation now that DI commutes with sup I, or with sup rather. So I can draw a commutative square if I apply the differential on this side, and I guess I didn't introduce a short notation for this. And I apply this function DI on this side, and I take supports. Then this commutes, because I'm in characteristic 0. And that's going to be useful, but I'm not going to need any other sort of algebraic properties of this map DI as such. So that is the setup. Those are the basic objects. Now, what the main result is going to be is a sort of differential version of the fundamental theorem of algebraic geometry, which says that the fundamental theorem of tropical algebraic geometry, I suppose, says that if I have a tropical polynomial equation and a solution to it, I can lift this to a field-valued solution to a field-valued equation that tropicalizes to my given tropical one, or I can do this at the level of ideals as well. So that is sort of the shape of the main theorem here. There's a few subtleties to the main theorem, so I want to build up towards it. I'll start by saying, well, okay, what do we want to do? Well, okay, let me just do a few examples of, maybe I'll just do some examples of these operations on B adjoint T to show that although the differentials commute with the support map, most things don't commute with the support map. The support map, tropicalization is not functorial, as something people say about this. Tropicalization doesn't preserve, doesn't intertwine with a lot of the other ring or semi-ring operations you could do. So just to show a few of the kind of standard tropical phenomena that go wrong here, or that don't commute anyway, one thing is that this submap is not multiplicative. So for instance, if I just take, let's say, in power series in one variable, that'll do. If I just take, the product of, I'll write it as evaluating a polynomial because I'll want to be thinking of evaluating polynomials later. If I just take the product of 1 minus t and 1 plus t, I get 1 plus t squared. Whereas if I kind of do this tropically, and I want to, well, the support of both of these things is 1 plus t, they have a constant term and a linear term, then I will get, sorry, this is 1 minus t squared, of course, not tropical yet, but here I will get a linear term. And so, you know, here is a case where this is not the support of this. So the support map does not send that to that. So here's a failure of multiplication to intertwine with the support map. You could say that generic lifts of these two things will multiply to have a linear term, but I've chosen my list so there's no linear term. So multiplication doesn't intertwine with the support map. Or typically, you know, the differential doesn't intertwine with the support map. So if I have a differential equation, something like, again, I will just do a ordinary differential equation. Let's take something like t times x1 prime, which I guess I am writing as x11, minus a times x1 no derivative, where a is going to be some natural number. Let's say a is greater than or equal to 0. A is strictly greater than 0, natural number. And if I want to evaluate this at t to the a, that's classically a solution. But tropically, we have a cancellation that if I just naively evaluate this thing, right, so I can kind of do all of this stuff formally in tropical polynomials adjoin a single differential determinant. And sorry, this tropicalizes to just a tropical sum, and the coefficient goes away since it's a strictly positive number. And then if I try to evaluate this at t to the a, which I can do, well, I'm going to get t to the a plus t times t to the a minus 1, because this is a shift operator. That's t to the a plus t to the a is t to the a. And again, there is a cancellation of two terms over my field, which wasn't detected tropically, so this doesn't intertwine with the support map as well. So this second example shouldn't cause too much consternation to people who have done tropical things before, because if I want to detect tropical solutions, all this says is I can't just evaluate a tropical polynomial or a tropical differential polynomial and expect the output to be 0. I'll have to do something like probably make the minimum of something appear twice. That's what the normal expedient in tropical commutative algebra is. It's certainly not just evaluating polynomials and observing that they don't commute. So, of course, the differential theory has the same sort of behavior. It might be concerning here that, well, the solution to this equation is supposed to be t to the a, tropically as well. I guess you'd like it to be t to the a, but a has vanished. A was just a coefficient, and now the tropical equation doesn't remember any information about a. So that's a curious phenomenon. And, well, the way we'll deal with that is by working with differential ideals and not single polynomials in the end. And then the differential ideal will contain the 8th derivative of this, which will have a anomalously small support. And that's how this differential ideal will remember the a, even if this equation didn't remember the a. Preview of the theorem, but for now, this is just to motivate the usual sort of mode of developing these tropical algebraic theories where I look at tropical solutions, is that, well, okay, to find a tropical solution, I don't just want to naively substitute, I want some kind of minimum attained twice condition. So, okay, what did this do? I guess, what does it mean to evaluate? How should we evaluate a tropical differential polynomial? Given that we are trying to follow the sort of non-differential tropical pattern, where we evaluate it term-wise, and then we check if the minimum or maximum, depending on your convention of choice, is attained 2 or more times among the evaluation of the terms. We'd like to do something like that. There's a bit of a complication here. So the first complication is that we're actually going to need to invoke 2 different semi-rings in the statement of the theorem. One of them is this ring of differential power series. Boolean sum, you're going to join a bunch of differential variables. And the other is, okay, so we need a second. For now, I will just call it blackboard bold S sub m, and it's going to be a quotient of this tropical power series ring by some operation, which I'll define later. I want to get to the statement of the main theorem, so I'm postponing some of the definitions. So this is to be defined. I'll come back to it. But the point of this is that I want to quotient away the failure of my support map to be multiplicative. So that's what this is for. I will call this the valuation, imitating the notation in the papers. So if I compose my support map with this quotient, so if I define the valuation of something to be, well, the equivalence class under this quotient of its support, as defined above, then I want this to be multiplicative. My example showed that multiplication in this power series ring is not, or the support is not multiplicative on the nose. That's what's shown by this first example up here. So I can take a quotient that will make it multiplicative, and that will be useful for the purposes of evaluating my differential polynomials term-wise. As I say, I'm postponing the partial differential definition of this, but I will give you just the univariate version straight up. So the univariate version is just going to be the t-adic valuation. When there's one differential variable t, this is just my t-adic valuation. So this, well, the image of power series, not Laurent series under the t-adic valuation, are the natural numbers which sit within the tropical numbers, however you like to think of the tropical numbers. I guess I'm thinking of the min plus tropical real numbers here. But within them we have these natural numbers, and I have the t-adic valuation. So I'll give the general definition later, but think about ordinary differential equations. I really am just taking t-adic valuation, and t-adic valuation is multiplicative. So this achieves the effect I wanted. Okay, so with that sorted out, I can now try to evaluate terms of tropical differential polynomials. So what should this mean? Well, I want to evaluate a polynomial term by term at some, well, some tropical object. So if I had a genuine differential polynomial in characteristic 0, I'd want to evaluate it at some power series value of the variable. So I have m coordinates of my power series, n differential variables. So I have an n tuple of m variable power series, and this is what I need to evaluate a differential polynomial at. This has a tropical counterpart where I take the supports of this. I'll call that S, following the notation in the papers. So this will be the support coordinate-wise. So the support of phi 1 through to the support of phi. And this is just a tuple that lives in, oh, I've sort of run off the edge of the page. This is going to live in my power series to the n. And so I'd like a way to evaluate a monomial of the sort that might appear in a tropical differential polynomial at such a thing. A typical monomial in a tropical differential polynomial looks like this. Again, this is notation from the papers. Capital M is just some indexing thing. So there is an element, there's a coefficient, which lives in my ring of power series. And then I have possibly a monomial in all of my algebraic indeterminates, which are all of these derivatives of my differential indeterminates. M is some kind of big 3 tensor or n+1 tensor that indexes the monomial in my differential indeterminates. This will be an notation for an arbitrary term of a differential polynomial. Now what I want to do is evaluate this term at my supports, at my tropicalized power series. And this is, how I do this is going to make clear why I need the second semi-ring. So the fact is that this data S determines the valuation of my term, but I want the differential indeterminates to be my phi. How is that? Well, I take the val, so I take this coefficient in my quotient semi-ring, and then I also have to take these derivatives. This is a product of my tropical differential operators. I have to take these derivatives before quotienting, then move to the quotient semi-ring. And so in order to make the tropicalization of the evaluation of one term of my polynomial actually be determined by the tropicalization of the point I'm evaluating at, this is why I need these two semi-rings. I need to use the unquotiented semi-ring here so that the differentials are defined. The differentials won't be well defined on this SM, but then I want to take products, and for the products to be well behaved, then I want to move to the SM so that the multiplication behaves nicely. So I say this because this is the part of the theory it took me the longest to get my head around. So this val of the evaluation of a single term, I'm going to set up my evaluation of tropical differential polynomials so it matches this thing. So now I make the rest of the definitions to match this. So I want to say that I tropicalize my term to, well, all that I'm going to do is apply this valuation map to my coefficient. I'm going to leave the monomial as a tropical monomial that looks the same way. So the tropicalization of my term is going to look the same. And then I want to define the evaluation of my tropicalized term at this datum S to be this quantity star. Okay. With this, we're most of the way to the theorem, I think. I've defined what it means to tropicalize a term. I want to extend this definition linearly. So extend this linearly. Extend the definition of trop linearly. This tells me how to tropicalize an arbitrary differential polynomial now, right? So if I have an element of my differential polynomial ring, I write it as a sum of terms over some m of some tm and now this is the sum in the tropical differential. semiring. And given one of these things, I also extend the definition of this evaluation map linearly. So now I can, well, okay, never mind. I don't need to do that because I don't want to evaluate a whole tropicalized polynomial. Really, the tropicalized polynomial is just some kind of data structure for collecting its terms, and we're going to have a different definition for when a tropical polynomial vanishes. That's not just evaluating the terms and summing them, it's evaluating the terms and doing something else. So again, because I haven't told you what my quotient semiring is yet, I can't exactly tell you this definition. So to be defined, is when does a sum of these tropical terms vanish. But I can give you the ordinary differential equation version. If m equals 1, it's what you expect. In this case, we had the ordinary tropical numbers. And in this case, we have a sum of terms, that this sum of terms vanishes if the minimum is attained at least twice. Oh, and I wasn't on the screen. So again, I want to state the theorem so that I don't not state the theorem. So I'll come to what the partial differential version is afterwards, but the ordinary differential version is going to be that the minimum is attained at least twice, and we have some definition of when a formal sum of terms vanishes in other cases as well. Okay. We're getting near the theorem. So what I want to say, well, now we can say what it means to be a solution of a tropical differential equation. So I can use this evaluation apparatus I've just set up and say that if I have an element of my tropical power series, an n-tuple of elements in my tropical power series ring, that's the kind of thing I have to evaluate at. This is a solution to some polynomial, which is going to be a formal sum of terms in my tropical differential semiring if it vanishes when evaluated at S in this sense. F evaluated at S vanishes according to the definition I've given above. And the point of this whole theory is that I've constructed it so that at least vanishing descends from the characteristic 0 power series setting to this setting. So the point of all the definitions I've given is that if I have a solution a tuple of power series and an element of my differential polynomial ring, and I substitute and I get 0. In other words, if, oh, I'm off the bottom again, sorry. if I have a differential polynomial, a tuple of power series, so that the evaluation is 0. That is, phi is a solution to the differential equation f. Then also, if I tropicalize these things, and the tropicalization of this f also satisfy the same. Okay. Maybe this is a good time to, in fact, probably it's too late to pause for questions, but I will pause and just check if there are any questions on the setup, because this is, I'm about to state the theorem. The theorem will be a converse to this under the right conditions, but the setup is meant to make this part of the theorem be the easy direction. So I'm just looking at the Zoom chat, and I'll wait a second just in case there are any questions there. If you see anything, Andrea or Jerome, you can mention it. Okay. I don't see anything. Okay, so there's a fair amount of setup. But now, as I say, so this is meant to be the easy direction of the main result. If I have a solution to a classical differential equation, then I have a solution to a tropical differential equation, the way I've cooked these things up. And the main theorem is a converse under the right conditions. Okay, so the main theorem, this is, well, okay. I've collapsed two historical things together. The ordinary differential and the partial differential versions. The ordinary differential version is due to, for instance, Iroka, Christian, Garay, and Zainab Doani in 2016. And the general version is due to Falkensteiner, Garay, Hayesh, Noatman, Torani, and Boulier in 2020 at a little conference we ran in December at Queen Mary about these things, so with input from various other people at the conference too. It was a big sort of joint effort work. These six wrote the paper. So, all right. Now, in addition to my characteristic 0 assumption that I've needed the whole time, I now need this thing to be algebraically closed, and I need it to be uncountable. Both of these are actually essential hypotheses. I also need to work not just with a single differential form, but with a differential ideal. And then we can do this, we can state the converse to this. So if I say I haven't defined the word solution. Okay, well, I'll state it. I will write the theorem using the word solution. If S in my power series ring, tropical power series ring to the n, is a solution to I, then there exists a characteristic 0 lift of it. Oops, and this should be trop I. This is a solution to trop I, and there exists a lift of it. I should introduce the notation. This is phi as a solution to f. And this is sup phi as a solution. I said this, but didn't write it down. trop. So this is a converse if we have an uncountable algebraically closed field of characteristic 0 and we're working with a whole differential ideal. Those are the conditions under which the converse attains. So that's the big theorem. In the rest of the talk, I want to fill in what the other semi-ring is, which I haven't told you yet. I want to say a little bit about the proof, and then I'll see how tired people are and maybe say a bit more about why the assumptions are necessary or about initial ideals or bases or things like that. Good. All right. So let's go back to this semi-ring. All right. What is this SM? So this is sort of done by hand in the 6th author paper, but it has precedence. And I know that Andrew McPherson did it. I don't know if he's the right name to put here either. There are probably earlier precedents for a statement like this. Basically, I just want to take the coarsest quotient, which makes my semi-ring cancellative. So if I have two elements of my tropical polynomial semi-ring, I want to say that they are related by this relation if there is another element such that the products are the same. So if I quotient out by this, I will have a nice cancellative semi-ring. So for all C in here. Well, then what is this thing? Sm, which I define to be this quotient, is isomorphic to. Well, okay, I'll say this two ways. One is I want to view this as a semi-ring of support functions, of tropical polynomials. So piecewise linear convex functions from the naturals to the naturals with natural coefficients. So, okay, this is going to be a semi-ring of functions. With pointwise min and plus as operations. And, well, which functions am I going to use? I'm just going to use functions that are minima of linear functions. So I want functions that can be written as if I have a tuple y of natural numbers, I just send them to the minimum of a collection of linear functions. And there might be some number, 0 or more of these terms. The collection of such functions, these are piecewise linear convex functions. And I meant to say that the A's are in N, sorry. These are piecewise linear concave functions. So they form a semi-ring, and that thing is isomorphic. And the isomorphism is just that I send for each element the support of my tropical differential form. So if I have a tropical differential form, I'll write it as the sum over a set of exponents that actually show up. So A is a multi-index, a set of multi-indices. A is a subset of n to the m. What is its class under this relation? Well, I just send it to the function where I use these exponents that appear as the coefficients of my linear function. So the effect this has is that certain of the exponents will have the potential of being the minimizing term, being the unique term that minimizes this minimum, and others don't, and the ones that don't, their presence doesn't matter. So that's what this equivalence relation says. I can say this in an even more combinatorial way, which might make this more helpful. So I can also view this as a set of polyhedra. It's also isomorphic too. Now I want to say it's isomorphic to a certain set of polyhedra. So this is, well, what do I want? I want kind of Newton polytopes, except that because I'm working in power series, I want to take the Minkowski sum with the positive orthant right away. So the polytopes I get are the polytopes whose recession cone is the whole positive orthant and which live in the positive orthant. And now, okay, well, union and Minkowski sum are my operations, except I can't literally take union. I have to take the convex hull after I do the union, and then Minkowski sum. That's another way to present this semi-ring. So this is the semi-ring that features in the theorem. When m equals 1, what's happening here? When m equals 1, then the support of a power series is a subset of natural numbers. I have one coordinate, and then I take the minimum of the linear functions, a times y, where a is in my set. And, well, that's just determined by the minimum element of my set. If a is the minimum element of my set, then the term ay will dominate all other terms. And so the function I get here is just a times y. And so the class here is determined by the minimum element of the support of my power series, and that is the t-adic valuation. So that's why this thing reduces to the t-adic valuation in the case m equals 1. But I mean, it's also nice and concrete what you can do if m isn't 1. So if m equals 2 and I have something like t1 cubed plus t1 cubed t2 plus t1 t2 squared plus t2 cubed, and I want to look at the class of this in here, then, okay, what is this? Well, the polyhedral picture is that I've got these 4 coordinate monomials, 3, 0, 3, 1, 1, 2, and 0, 3.
Alex, we cannot see.
Oh, sorry, I went off the bottom again, thank you. Thank you. Okay, I have this polynomial in B adjoined T1 and T2. Power series, in fact, it is a polynomial. And I want to say what its class is, where it maps to under this quotient. So here are the 4 exponent vectors in this thing. And I want to construct the Newton polytope, except adding in the whole positive orthant of the recession cone. And so what I get is this red polytope. And so we can see that the 2 terms that have a chance of determining the minimum of an affine function, a linear function on this polytope, the 2 places where the minima can be attained if it's attained at a single point are here or here. So kind of the 2 key terms are the extremal terms, so that's another element of this, and both are represented by this polytope or by the support function of this polytope. And with that, we can now also say what it means for a sum to vanish. Now I say that a sum of terms, this is the other piece I left out before presenting the theorem. If, well, I've given you 2 isomorphisms, I can say it in either one. So if the minimum is attained twice pointwise in, let's call this double star in this support function perspective. Let's call this double star. So support function just want them to return twice pointwise, or every vertex appears twice. In this polyhedral perspective. All right. I see it's 10 to 3. Oh, there is a question. In the proposition, do I mean to write that there exists C so that AC equals BC for all C? No, I meant to write for some. Thank you. Thank you, Adam, for catching my typo. Yes, I meant to write for some C. Perhaps this is the right time to stop. I am happy to take questions about the proof of the theorem or other things that I said I might say and didn't say, but I'll stop here. Thank you.
Okay, so thank you very much. So you answered, yeah, Adam's questions. Do you?
I actually have a question.
Yes.
Andrea?
Thank you, Alex, for the talk. I actually have just brought the question on Zulip. We can discuss more in detail in a moment, but the question is the following. So if I give you, in your context, if I consider only one variable, I can consider a linear operator, so something written as sum fi d power I, where d is the derivation, and fi are power series in one variable. So so let me consider this operator as an endomorphism or of the ring of power series.
Yeah.
And then to that object we can associate actually a polygon by just looking to the t-adic valuation of the coefficients. This is a classical polygon. So the question is, can you recover that polygon using your theorem?
So the first, to figure out how to make the question well defined, I'd have to figure out how to get an endomorphism of the formal power series ring into the theorem. And that's something I'd have to think about how to do because, as is usual with these tropical things, the choice of the monoid of monomials and the action of the differential on it is baked into this. And what happens when we change that? I think if we could globalize this theorem, then there'd be a way to do it, but I don't immediately see how to get the theorem to consider this operator at present.
Yeah, there is a difference actually, because your context is completely commutative, right?
Mm-hmm.
And the endomorphism ring, so it's not commutative.
Yeah.
The derivation doesn't.
So in the endomorphism ring doesn't literally appear here at all, and it's I don't know tropical non-commutative algebra very well.
Okay, thank you very much.
I don't know if there is tropical Does anyone have tropical non-commutative algebra? But it's a good question. I should think about it.
Yeah, thank you.
Yeah asks, why is it important for the field to be uncountable? Oh yes. What can go wrong if the field is countable? There is a paper of Denef and Lipschitz from 1984, which talk about computability in, computability implications of solutions to differential ideals. And they have theorems that say things like, any computable power series over Q is the unique solution of some algebraic system of PDEs. And so given that, you can construct a ridiculous, computability reduction style algebraic system of PDEs, where you take every polynomial, you take some computational enumeration of every what do I say? Set of polynomials, one that vanishes at every element of your field, which you can do if the field is countable. Throw all of those things into a single polynomial, into a single power series rather, and then write down a differential equation that demands that the support of this power series be complete. And if the field's countable, there, just aren't enough elements. Every element is going to make the support of this power series vanish at some point. So it's these weird computability obstructions which go wrong in some sense.
Okay.
It's used in different ways in some of the proofs in the literature, but I thought for a long time it was removable. I think I talked to you about this, trying to remove this. So, sorry, any other questions?
No, so I don't see any other questions, so you're welcome to ask them later in